Okay, hello and good morning, everybody. Welcome to our class. In the last class, we discussed the chapter 6 problems and how to solve chapter 6 problems, kinetics of rigid bodies. And today we will start solving exercises. And the first one I will solve for you slowly with a whole lot of explanations. And then you'll have time to try solving these type of problems on your own with support from my side, of course. So let's have a look at the first exercise. It is exercise 6.6. Just move the chat over here. Okay, so what do we have? We have an eccentrically loaded thin beam. Mass and length of the beam are given. And this is the depicted position is our initial position, rest position, and then it is released from this rest position. It is dropped, and we have to find the angular velocity and the angular acceleration during the oscillating movement. We can neglect the friction and air resistance. Then in the second step, we have to find the velocity of the center of gravity and the acceleration of the center of gravity. And third part is defining the load in the bearing, support reactions. So how do we approach these kind of problems? First of all, we need to draw a free body diagram. And our free body diagram always has to be drawn in deflected position. This means that this is our original position. I will draw it with a dotted line. So like this. Let's assume that this is the position of the support. And now to include all the loads correctly in our equations, we have to consider the system during motion, meaning in deflected position. So the beam is dropped and then it starts to rotate about this the support, meaning that it swings back and forth, something like this. Okay, that's the motion. And now we draw this the support this beam in an arbitrary position, somewhere, some position during motion. So maybe like this. This is the center of gravity. That might be here. And for the deflected position, we include all loads acting on the system, meaning that we have support reactions in our support labeled with D. It's a hinge support. Then we have two support reactions in normal and tangential direction. You could also draw the support reactions in horizontal and vertical direction. This would also work. This would also be correct. Okay. Then what else do we have? We have to consider gravity. Due to the mass of the beam, mg. Then in green, I will draw the motion of the beam. These are not loads, okay? Only red vectors are loads and will be considered in our equilibrium conditions, but we need to describe the direction of motion, because in this depicted position, the beam could move upwards or downwards, this way or that way. We have to choose a direction. And depending on our choice, we can draw the inertial loads. Then, due to the rotation, we have to consider the inertial moment opposite to the direction of the angular acceleration. JC times alpha. And we have to consider the inertial forces, which always act in the center of gravity, and they point opposite to the direction of acceleration. What kind of acceleration do we have in the center of gravity? The center of gravity moves along a circular path, meaning that we have a tangential and a normal component of the acceleration. In consequence, there are two inertial forces, one in tangential and one in normal direction, opposite to the direction of the tangential and normal acceleration. So this would be m times e times alpha and me omega square. Mass times tangential e alpha or normal e omega square acceleration. E is the distance from the center of gravity to the point of rotation as defined in the script and as we discussed in our last class. So this from here to here is E, the distance E.
Professor, I have a question.
Yes.
This JC alpha is for the general motion, right? Rotational motion.
Yes.
So doesn't it include all the points on the body? Why do we have to take separate inertial forces for the center of gravity?
Yeah, that's what we discussed in our last class. Our general approach for the general motion of an object always includes the inertial forces in the center of gravity and the inertial moment with respect to the center of gravity. So if we always break it down to these two parts, inertial forces in the center of gravity and inertial moment with respect to the center of gravity, this fulfills the requirement for any arbitrary motion. Translation plus rotation, because that's what our approach says. We describe a general motion as translation as one point plus rotation about this point, the center of gravity in this case.
Okay, thank you.
Yeah, you're welcome. Then when we build the equilibrium of moments, our JD, the mass moment of inertia with respect to the current axis of rotation, consists of JC times alpha, inertial moment with respect to the center of gravity, plus the inertial force multiplied by lever arm, which is equal to the Steiner shear. We will see this later on. Okay, so E, we can read E, the distance from center of gravity to the support from our figure given in the problem description. This is L over 4. Then we need to find JC, the mass moment of inertia, with respect to the center of gravity. And for this, we have a look to the formulary on page 6. So what do we have? We have a long, thin rod, and the mass moment of inertia with respect to the axis J or C is 1/12 m times L squared. So that's the mass moment of inertia that we need, 1/12 m L squared. Now in the first part of the problem, we have to find alpha and omega, angular acceleration and angular velocity. And our angular acceleration is depicted in our free body diagram. So first, let's check how many unknowns we have in our free body diagram. I'll just state it here. Unknowns are the support reactions, angular velocity, and angular acceleration. All other values are given. Now we have 4 unknowns, but there are only 3 equations available, 3 equilibrium conditions that we can state for this system, meaning that we cannot solve the system for our unknowns. So we have to find another equation to solve, like a 4th equation to be able to solve for all the 4 unknowns. So let's start with the first equilibrium condition. And I would recommend to build the equilibrium condition equation of momentum with respect to the support. Of course, then we do that, there will be only one unknown in the equation. 0 is equal to JC times alpha plus ME alpha times E, lever arm, and the component of gravity. So we need to define an angle between the initial position and the current position of our system, of our beam. So this angle can be found here as well. And then we can decompose the equation. We can decompose the force of gravity, mg cosine phi times E. Then rearranging the equation for our unknown value alpha, we obtain JC plus ME square times alpha is equal to mg E cosine phi. And this here corresponds to our mass moment of inertia with respect to the axis of rotation, D being the axis of rotation in our specific problem. Now we can substitute the mass moment of inertia, the center of gravity, and we can substitute E by L over 4. There's a question in the chat. Initially, we never had an angle. Why decompose? Well, because if this is the point D and this is where the force of gravity acts, this is our lever arm, right? And we do not know this lever arm. So we need to decompose either the lever arm using the angle or the force of gravity. And if we use this component of the force of gravity, we decompose the vector like this, then this, whoops, this would be the lever arm. Distance E, and this is mg cosine phi. Lever arm always has to be perpendicular to the axis of rotation, to the vector, the force vector. Okay, so JC is 1 over 12 mL square, and E square is L square over 16, 4 times 4. Then this is 7 over 48 L square. Okay, then let's substitute this into the equation, and we obtain 7 over 48 ml square alpha equals mg e, which is L over 4 cosine phi. And the mass cancels, and 1L cancels, and we have alpha angular acceleration as time-dependent variable with 12 over 7 g over L cosine phi, and of course the angle is time-dependent since the position of the beam changes over time. It's swinging back and forth. So this is our first result. The angle during the oscillating motion. And as you can see from the equation, our angular acceleration is not constant. Now, we have to, second step, we have to find the angular velocity, omega. And for this, we have two options. The first option you might think of would be integrating alpha to obtain omega, which is possible, but it cannot be directly done since alpha depends on the cosine of phi as the time-dependent variable. So multiplying this term by the time does not equal omega. So how do we integrate this equation? This is our option 1 for obtaining omega. Integration. So in general, we know that alpha is the time derivative of omega, time derivative of the angular velocity. Now, our specific angular acceleration depends on the angle phi. Now, we can extend our time derivative using this angle, multiplying by 1, not changing the equation. So if we state the equation like this, we multiplied by 1, so this does not change our equation, but now we have one term being the time derivative of the angle, which is our angular velocity, and we have the time derivative of the angular velocity, not the time derivative, the derivative of the angular velocity by the angle. So this is d omega over d phi times omega. Now, we multiply this equation by d phi, and we obtain omega. The omega is equal alpha d phi, alpha being time dependent. And now we integrate both sides of the equation. We start from rest position, then angular velocity and acceleration are 0, and we will integrate through an arbitrary position, omega and phi. Now, integrating omega over omega is 1/2 omega squared. And integrating alpha, this equation here, is an integration of the cosine of phi. Then we have 12g over 7l, which is constant. Do not have to integrate that. Cosine phi d phi. Then this is 12g over 7l. And the integration of cosine is sine phi. And now we rearrange the equation to obtain omega, multiplying by 2 and taking the square root with 24 G over 7L sine phi. So this is one option solving for the angular acceleration. And this is our fourth equation that we need to solve for all the unknowns in our free body diagram. There's a second option to find the or to define the fourth equation to find omega without using the equilibrium conditions. And this is using energy conservation law. So how would that work? Option 2. Energy conservation law. In general, we have E0 plus work added is equal to E1 plus work extracted plus work performed due to friction. In our system, there's no work added, there's no work extracted, and we can neglect friction. So we're only left comparing energies. What type of mechanical energies do we know? We know potential energy, kinetic energy, and spring compression energy. There's no spring in the system, so we are only left with potential and kinetic energy. Then for the potential energy, we need to define a zero level. If this is our starting position, then later on will be here. This is the center of gravity. Then, for example, our zero level could be here. Could be in the previous position as well. It will give the same result. And this is situation E0, and this is situation E1. Okay, potential energy. We do have potential energy in the first situation, but no kinetic energy since our system is at rest. So there's no velocity in the system. But we need to find this height to describe the potential energy. mgh. In the second position, E1, the potential energy is 0 since we are in the zero level, but our system is moving, meaning that we do have consider kinetic energy. Then this would be 1/2 jc omega square plus 1/2 v square, the velocity, which is e times omega square. So our height can be derived using the angle and the distance e. Then h is equal to e times sine phi. Now, if we substitute this into the equation, we have m times g times L over 4 sine phi, which is equal to, well, again, this the same as stated above. 1/2 jc plus me square times omega square. This is jd, which we computed at the beginning, at the very beginning. Then we have mg L over 4 sine phi is equal to 1/2, then 7 over 48 L square omega square, again, mass cancels, one length cancels. And we can rearrange for omega, which results into 24g over 7l times sine phi and square root of this. And of course, we obtain the same result as when we used option 1. Has to be identical. Okay, so both is possible. You do not have to use energy conservation law, but it might be easier to apply than integrating a time-dependent angular acceleration. Okay, so this is our second result. Now, we are also asked to find the velocity and acceleration of the center of gravity. Then we can use our standard equation, page 1 in the formulary for a circular motion. So we see the velocity of the center of gravity in case of a circular motion is radius times angular velocity. We just computed omega. So this is L over 4 24g over 7l sine phi. We can move this L over 4 into the integral. Then we have 3 over 14 GL sine phi. Okay, and for the absolute acceleration of the center of gravity, we have to compute the tangential and normal component and then do the vector addition of these two components of the acceleration. AC tangential is equal to E times alpha. Which is L over 4 times 12 over 7 G over L cosine phi. And then this is 3 over 7 G cosine phi for the tangential component of the acceleration. And then the normal component is E omega square, which results into 6 over 7 G sine phi. Okay, and then building the absolute value of the acceleration of the center of gravity, ACT square plus ACN square. And we do not have a lot of possibilities to simplify this equation since it's dependent on the angle. What we can do is use this 307 place in times G outside of the square root. And then we have cosine phi square plus 4 sine phi square. So that's the second part of the problem. Okay, and the last part is the computation of the support reactions. And now we can use our two equations that are left from the equilibrium conditions to find the support reactions. Okay, so in my diagram, I drew the support reactions in normal and tangential direction. Then it would make sense to build the equilibrium conditions in normal and tangential direction as well. We have 0 is equal to dN minus the inertial force in normal direction minus the component of gravity, mg sine phi. And again, we can substitute for E, L over 4, and we can substitute omega square. Then this gives M, then 6 over 7 G sine phi plus mg sine phi, which is equal to 13 over 7 G M sine phi. That's the normal component of the support reaction. And then in tangential, the tangential component, 0 is equal to dt plus me alpha minus mg cosine phi and then dt is equal to mg cosine phi minus m3 over 7 g cosine phi, which is equal to 4 over 7 gm cosine phi. And then last step is building the absolute value of the support reaction by computing the square root of dn square plus dt square, which is equal to 1 over 7 mg, then 13 sine phi square plus 4, oops, cosine phi square. Okay, so that's how it works. Important things you have to remember is that you have to draw your system in deflected position, and then include all the loads acting on the system, including the inertial loads. There's an inertial, in case of a rotational moment, there's an inertial moment with respect to the center of gravity, and you have to draw your inertial forces into the center of gravity. Inertial forces always and only act in the center of gravity, never in a different position. Okay, that's important to remember. And then once you have your free body diagram, then you can build the equilibrium conditions, solve for the unknowns, maybe in combination with energy conservation law or an integration to obtain omega from alpha. If you have a constant angular acceleration, constant alpha, the easiest way would be integrating alpha over time to obtain omega. If alpha is not constant, then using energy conservation law might be easier. Okay. Any questions? Okay, if not, then you can try to solve, or you can solve a problem on your own. I will discuss the problem first. It's exercise 610. Okay, so this is not part of the problem. That's from the problem above. Okay, we have a cylinder with a given mass and radius, which is set in motion from standstill by a driving moment of 6 Newton meter. And we have to find the minimum coefficient of static friction between cylinder and surface, assuming that the cylinder rolls without sliding. And in that case, we have to find the acceleration of the center of gravity. The gravitational acceleration is given with 10 meter per second. So again, what do we have to do? We have to start solving this problem as you learn to solve the problem in statics and engineering mechanics 1, meaning that we draw a free body diagram, including all loads acting on the system. So in this case, we have this cylinder with the center of gravity. Now, first of all, we will include all the static loads, like drawing our static system. Then we do have gravity. We do have a normal force. And we have a force of friction. And as an external load, we have to consider the moment ma. Since this moment is driving moment causing the motion, our cylinder rolls clockwise and this direction. So this is our like a simple system, like the tire problem and rolling cylinder problems that we discussed in chapter 2 already. And now we solve this not for kinematics, but for kinetics, meaning using loads. Since we have a driving moment given and we have to find the coefficient of static friction, these are all values that are part of a load or that are a load. A moment is a load, and the static friction coefficient is stated in the equation for static friction. This indicates that we have to use kinetics, that we have to compute loads of the system. Then we have to include our inertial forces. Our inertial forces act opposite to the acceleration. Then, since our cylinder rolls clockwise, we have an inertial force, Jc alpha, acting opposite to alpha, acting counterclockwise, and the cylinder rolls to the right. Then our inertial force acts in the center of gravity, pointing to the left. Like this. Now, how many unknowns are in the equation? Ma is given. The mass of the cylinder itself is given. The gravitational acceleration is given. There's a relation between normal force and force of friction, which we can only use in the limiting case. Our situation is not, it is discussing the limiting case since we have to find the minimum coefficient of static friction. Then we do not know the acceleration and we do not know the angular acceleration. But we have the information that our system rolls without sliding. And this means that we can apply the kinematic condition. So we need to state the kinematic condition of a rolling cylinder, which we did several times already in all these previous problems with cylinders and tires. And with this equation, with this additional kinematic condition, we can solve the system. No, the friction does not face to the left because our cylinder is driven by the moment. And if the moment increases and is too high, then the cylinder would rotate faster than it translates. And therefore, the force of friction acts opposite to the rotational motion. Okay, this is the surface. By what do I mean the velocity pole? Or the equation, the kinematic condition, yes. This is the direction of r omega, and this is the direction of the center of gravity, which in case of rolling is 0, of pure rolling is 0. But of course, if ma increases, which is our driving moment, the load causing the motion, then only if this increases the rotational motion, then the cylinder would start to slide, and then it would slide by rotating faster than it translates. And that's why our force of friction has to point opposite to the rotational motion. Okay. Okay. Any further questions, or is it clear what you have to do? Okay, and then I will open the breakout sessions. And
what up, y'all? Jacob Owens here for the Buff Nerds, and today I'm going to talk to you about how you can get the highest quality
kinematic condition, and then rearranging the equation for the unknowns: acceleration of the center of gravity and static friction coefficient. If you have any questions, then please call me into your session. You can choose your session on your own. Okay, and I will go through all the sessions as well, of course. Okay, I will start the session. You can pick sessions with your friends if you like. When there are any questions here in the main room, you can also ask. Okay, you can just write the question in the chat or ask when I'm here in the room, of course. Otherwise, I will not be able to read what you wrote in the chat. Okay, so the students in the breakout sessions are almost finished. So I will have maybe a bit less than 10 minutes time to solve the problem. Okay, there's a question in the chat, but I'm not quite sure what it's referring to. How do we know that the question deals with mass moment of inertia? We could have solved this second example without applying it here. Which second? This example with the cylinder, or what is meant by the second example? Yes, and well, the values given indicate what type of problem it is. Well, chapter 4 is a point mass. So, and we stated in chapter 4 the options when we can use the point mass approach. And then we said if we have a point mass, of course, an object without spatial dimensions, or a rigid body that is translating. But our rigid body has spatial dimensions, a radius is given, a mass that is not only located in one point, and our rigid body is rotating while performing a general motion consisting of translation and rotation. So this is not applicable with chapter 4, with the chapter 4 approach. We do have to use chapter 6, the general motion of a rigid body, and chapter 4 discusses point masses. Okay. Okay. At least the students who talked to me, I think they all came to a solution. Most of you should have finished solving the problems. Here you can see the equations that are needed to obtain the solution and the results. The acceleration of the center of gravity is 4 meters per square second, and the minimum static friction coefficient is equal to 0.4. Then just maybe one more thing, because I've been asked this a couple of times right now. This equation here, the kinematic condition, is only valid in case of pure rolling. When the cylinder starts to slide, this condition cannot be used anymore because it's not true anymore. One of the velocities will be greater than the other. So just keep in mind that in case of rolling, you can use the kinematic condition. In case of sliding, you cannot use the kinematic condition. And of course, in case of sliding, you would have to use the equation for sliding friction. Any questions? Okay, if not, then I hope that you all were able to solve this problem. And we will have a look at the next one, at problem 611, which actually refers to this one. There is a question, JC alpha and FRR be in the same direction? No. JC alpha is the inertial moment acting opposite to the acceleration, but the force of friction acts opposite to the velocity that is more likely to increase. So well, they are in the same direction because it's more likely that the cylinder starts to rotate faster than it translates, and that's why the force of friction is opposite to alpha.
Prof, I have a question. Did you take moments from the friction mu naught? Is that where you took your moment from? Hello, Prof.
You mean the equation of momentum?
Yes, where you have JC.
This
JC
equation
alpha,
right here.
Yeah.
I built this equation with respect to the center of gravity. That's why you see Fr times R in the equation. But of course, you could have chosen a different position. For example, this one right here would have worked as well.
Excuse me, Professor.
Oh, you mean it should be plus Fr in the equation? Okay, yeah, sorry, you're right, of course. Thank you. They are in the same direction. I thought we were talking about the diagram. Yes, thanks for the hint, for paying attention. Okay. Yes, so let's come back to the equation of momentum. I built it with respect to the center of gravity, but of course you could have also built it with respect to the velocity pole, for example. And it would have worked as well. You would have obtained the same result. You can choose the point of rotation. Okay, so let's have a look at problem 611. Which is this one right here. So this question refers to the cylinder from the previous problem. And now we have to describe the state of acceleration in case of sliding. So assuming that the friction coefficient is too small and our cylinder starts to slide with a sliding friction coefficient. Okay, now different situation, the cylinder slides, and again, we have to find the accelerations. Describe the state of acceleration. meaning acceleration of the center of gravity and angular acceleration. In case of sliding, the velocity due to rotation would be greater than the velocity due to translation, since the sliding is caused by the momentum. So we assume that R omega is greater than Vc. Then, and as I just said a few minutes ago, the due to this condition, due to this assumption, we cannot use the kinematic condition from the previous exercise. We cannot use the same equations. Okay, so just I'll give you about 10 minutes to solve the problem. You can still use the equations above from the equilibrium conditions. So the first three equations, they are still valid, but you cannot use this fourth and fifth equation. Okay. I will open the sessions again and then, yes?
Professor, I wanted to ask something.
Go ahead.
Since the body is sliding, shouldn't we neglect friction?
No, it's sliding friction that we have to consider now. We have a different situation, but the object is still sliding. So we have to consider sliding friction. Like in statics, you had these examples of blocks sliding downward, and then you had to consider sliding friction as well. It doesn't mean that there is no friction at all. That's not what it means.
Okay, thank you.
Yep. Okay, so this exercise was quite similar to the previous one, of course. The first three equations are identical. The fourth equation is the equation for sliding friction, which we can apply. And if we substitute our equilibrium conditions, equations 1 and 2, into the equation for sliding friction, we obtain the acceleration of the center of gravity with 3 meters per square second. And then knowing the acceleration of the center of gravity, we can use equation 3 to obtain the angular acceleration. Are there any questions regarding this exercise, the approach, or whatever, or any problems in understanding the problem description or what to do or something like that?
Yeah, maybe I have a small question.
Mm-hmm.
Couldn't we just consider this cylinder as a point mass since it doesn't have any rotations and it slides?
The cylinder does rotate.
But it also slides. Okay.
It slides and rotates, and that's why we do have to consider this part right here, the inertial moment. The sliding is caused due to the rotation because it slides faster than it rotates. So this is our starting position, and this would be the point on the surface. Then sometime later, this cylinder the cylinder might be here, translated over here due to the velocity vc, but it would have rotated much faster. So this point from down there would be here.
Yes, I understand. Yes, thank you.
Yeah, okay, you're welcome. Other questions? Because we have this equation here is the equation of sliding friction as learned in Engineering Mechanics 1. In case of sliding, you have to use the sliding friction coefficient, and it's always an equal sign, mu times Fn. Fr is equal to mu times Fn. And static friction, in our case rolling, okay, great. It's an would be Fr is smaller or equal mu0 Fn. And we can only transform this into an equal sign in the limiting case when it's asked for the minimum friction coefficient or the maximum driving force or the maximum angle of inclination, these kind of things. Only when we have such a question, we can use the equation of static friction and convert the smaller or equal into an equal sign. Okay, what we can do is we can prove whether our assumption is correct or not. So proof of our assumption where we said that R omega is greater than Vc. And our omega is equal to R, or if we build the time derivative, if R alpha is greater to than AC, and then our radius is 0.2 meter by 30 per square second. And then we had 3 meter per square second on this side. And yeah, you can see 0.2 times 30 is 6 meter per square second, which actually is greater than 3 meter per square second, meaning that our assumption was correct. Okay, then I have information regarding our class Monday next week, December 6th. There will be no class on Monday next week because I have a conference the whole day, almost the whole day. We will repeat that class 1 week later, so on Monday 13th. We do have a time slot of 2 classes on Mondays, which we used as and we used the second time slot as our offline class, which cannot take place right now anyway. So there will be no class on Monday next week, but then we will repeat this class 1 week later, we will have 2 classes on Monday in 2 weeks. I will send you a reminder via e-learning on Monday morning, just to make sure all of you read and have the information. Okay. If there are no more questions, then I wish you a good weekend, and we will continue from here Friday next week. So have a great day, good weekend, and see you next week. Thanks. Bye.